Continue on Physical Chemistry Chapter 2. We're beginning Section 6 now. We're going to talk about heat capacity. Heat capacity is a very important quantity. Now we talk about the heat capacity for a specific process. Subscript PR means process. So the heat capacity can be process dependent. And this is an uppercase C, which means extensive version. So the heat capacity of the process is defined as the change in heat transfer of the process, the derivative of the heat with respect to the process, divided by the differential of temperature. So the derivative of heat with respect to temperature. So capital C is equal to lowercase c times m. So remember, lowercase c is the specific heat, which is intensive. M is mass. So we have extensive is equal to intensive times extensive. Now, if the process is constant pressure, then we would put a capital P subscript for our process. So the heat capacity at constant pressure is equal to the derivative of heat at constant pressure with respect to temperature. And that's going to be equal to the partial derivative of enthalpy with respect to temperature at constant pressure. If the process is constant volume, then we use a subscript capital V. So we say the heat capacity at constant volume is defined as the heat transfer at constant volume divided with the derivative with respect to temperature. And that's going to be the partial derivative of internal energy with respect to temperature, holding volume constant. Now for closed system in equilibrium with pressure volume work only, we get, since we know that the heat at constant pressure is equal to the change in enthalpy, then we know the differential of the heat at constant pressure is equal to the differential of enthalpy. And likewise at constant volume, the heat is equal to the change in internal energy. Therefore, the differential of the heat at constant volume is also equal to the differential of internal energy. Remember, capital U is internal energy. The subscript capital V means constant volume. Now, the heat capacity at constant pressure and the heat capacity at constant volume, these have to be determined experimentally. So now, remember, we always like to keep track of writing our variables as functions of each other. So we know the heat capacity at constant pressure is a function of temperature and pressure, or the enthalpy is a function of temperature and pressure, or the internal energy is considered, this is a U by the way, capital U, is a function of temperature and volume, that's a capital V, and the heat capacity at constant volume is equal to a function of temperature and volume. Now, the heat capacity at constant pressure and the heat capacity at constant volume are also state functions. But the heat capacity at constant pressure and the heat capacity at constant volume are not the same. Like, don't subtract them and think you've canceled them out and got zero or anything like that. That's absolutely wrong. Now also, the heat capacity at constant pressure is not equal to zero, and the heat capacity at constant volume is definitely not equal to zero either. Both of them are positive. The heat capacity at constant pressure is greater than zero. The heat capacity of constant volume, that's supposed to be a V, got a little bit crooked there. See if I can make that neater. Probably make it worse, but anyway, that's a capital V subscript. That's also greater than zero. But they can be small. Technically, way beyond this class, there are cases in cosmology where you might actually come across a negative value, but that's irrelevant to this class. Now there is a material called graphene, by the way, that's transparent, light. It's even harder than steel, but it conducts electricity like copper. I forgot what that has to do with this class, probably because I was talking about heat transfer. So what we said that the heat capacity at constant pressure minus the heat capacity at constant volume is not equal to zero. Well, then what is it equal to? Well, it would be the partial derivative of enthalpy with respect to temperature at constant pressure minus the partial derivative of internal energy with respect to temperature holding volume constant. Now remember, H is equal to U plus PV. So, substituting that in, we get Cp minus Cv is equal to the partial derivative of U plus PV with respect to temperature, that's the partial derivative with respect to temperature, at constant pressure, minus the partial derivative of U with respect to T at constant volume. So then, splitting this out, remember when you're adding, you can split them out all you want. Let's see here. So Cp minus Cv is equal to the partial derivative of U with respect to T holding pressure constant, plus P times the partial derivative of volume with respect to temperature holding P constant. Remember, we can pull, when you're doing a derivative, you can pull a constant out. We're at constant P, so we know this P is constant. We can pull it out. That's how we were able to pull this P out in front of the derivative right here. And then, of course, this comes down, minus the partial derivative of internal energy with respect to temperature holding volume constant. We're going to refer back to this later, so we'll call this equation 1 for now. What we want to do is substitute out for this term here. Now, we said that internal energy is a function of temperature and volume, so we're going to write the exact differential. So don't confuse the U with the V here. The differential of U is the partial derivative of U with respect to T holding volume constant times the differential of T, plus the partial derivative of U with respect to V holding T constant times the differential of volume. Now, we're going to assume for now that P is constant. So to show that, we've put the subscript P here. We can do that, but remember then this is constant P and this is constant P too. So now we have the differential of internal energy at constant pressure is equal to the partial derivative of internal energy with respect to temperature at constant volume times the differential of temperature at constant pressure plus the differential of internal energy with respect to volume at constant temperature times the differential of volume at constant pressure. Now we're going to divide all of that by the differential of temperature holding pressure constant. So we have the derivative, well, we have the differential of internal energy holding pressure constant divided by the differential of temperature holding pressure constant, and that's now equal to the partial derivative of U with respect to T holding volume constant plus the partial derivative of U with respect to V holding temperature constant times the differential of V holding P constant, that is V, right? Yeah. Divided by the differential of temperature holding P constant. So remember, these are both constant P, so we can just rewrite that as the partial derivative of U with respect to T holding P constant is equal to the partial derivative of U with respect to T holding V constant. This stays the same, partial derivative of U with respect to V holding T constant. These are both at constant P, so we can say that's the partial derivative of V with respect to T holding P constant. So we're going to refer to this as equation 2. So now what we're going to do is substitute this equation 2 back into the equation 1 that we came up with before. So now we have the heat capacity at constant pressure minus the heat capacity at constant volume is equal to the partial derivative of, shoot, I hope that's a U. Can't read my own handwriting. Yeah, the partial derivative of internal energy with respect to temperature holding volume constant plus the partial derivative of internal energy with respect to volume holding temperature constant times the partial derivative of volume with respect to temperature holding pressure constant plus pressure times the partial derivative of volume with respect to temperature holding pressure constant minus the partial derivative of internal energy divided by the partial derivative of temperature. Oh, that should be constant P. Whoops. No, wait a minute. That has to be volume. Where did... Yeah, that was constant volume. That was from the original equation. So I forgot a volume right there. Now notice these two terms are the same. It's a good thing that was volume then, because these two will cancel out. So we're left with this. Whoops. So coming up, so now we have the heat capacity at constant pressure minus the heat capacity at constant volume is equal to the heat capacity, or no, the partial derivative of internal energy with respect to volume at constant temperature plus P, because we factored this out. So all of that times the partial derivative of volume with respect to temperature holding pressure constant. See how we factor that out? So one thing you'll notice then, if we're adding these two together, they must have the same units. So just from this, assuming we've made no errors, we can say that the partial derivative of internal energy with respect to volume holding temperature constant has to have the same units of pressure. This term has a special name because it's that important. It's called the internal pressure. Now, none of these quantities up here is equal to 0, so we can't just cancel them out or get rid of them. So we know that if this isn't 0, this isn't 0, there's no way this difference can be equal to 0. So, like we already said before, the heat capacity at constant pressure minus heat capacity at pressure constant volume is not equal to 0. Or put another way, the heat capacity at constant pressure is not equal to the heat capacity at constant volume. Now, we already said that the heat capacity at constant pressure was defined as the derivative of the heat at constant pressure with respect to temperature. So this is the heat added at constant pressure. Subscript capital P means constant pressure. Likewise, the heat capacity at constant volume is defined as the heat flow at constant volume divided by the differential of temperature. So this is the heat added at constant volume. Subscript capital V means volume. Now we also know from before, because of the type of systems we're looking at, that the differential of the internal energy is equal to the differential of the heat plus the differential of the work. So we're going to say the differential of the heat at constant pressure is equal to the differential of the internal energy at constant pressure minus the differential of work. And that's equal to the differential of the internal energy at constant pressure plus PDV. Remember, double negative makes a positive when you're multiplying. Since we substituted in using differential of work is equal to minus pressure times differential of volume. Likewise, the differential of heat at constant volume is equal to the differential of the internal energy at constant volume minus the differential of work. But remember, we're going to say dW is equal to 0. Oh, because we're talking about this is constant volume. If this is a constant volume, there's no work. So at constant volume, the differential of heat at constant volume is equal to the change in the internal energy. Differential of the internal energy at constant volume. So the reason that dQp or dQv are different is because dQp, it includes expansion work, but dQv is just increasing the internal energy. It doesn't include the expansion work. Now dQp then is not equal to dQv. Remember this, so constant pressure, constant volume. And likewise, the differential of the internal energy at constant pressure is not equal to the differential of the internal energy at constant volume. Now, we can say that the heat capacity at constant pressure minus the heat capacity at constant volume is proportional to the differential of the heat at constant pressure minus the differential of the heat at constant volume. But it's equal to the differential of the internal energy at constant pressure minus the differential of the internal energy at constant volume plus PDV at constant pressure. So when we're talking about gases, this PDV at constant P is the important term when we're talking about gases. So if we have gases at low pressure, the internal energy is roughly 0, or at least the change in internal energy is roughly 0, because the intermolecular forces are not going to be changing that much, and it's those forces that's basically storing the energy, the conservative forces. But the du term, the differential of the internal energy term, that's what's important for solids, liquids, or gas that has high pressure, because then the intermolecular forces, the attractions, you're storing energy there, internal energy. Now, so basically, differential of the internal energy at constant pressure and differential of the internal energy at constant volume, you need to pay attention to that when you're talking about the condensed phases, liquids and solids. That's internal energy we're talking about, obviously. Now, solids and liquids can have internal energy because the molecules are close enough to have intermolecular attractions. I think I already said that. So this concludes Chapter 2, Section 6.